Okay, hello everyone. Welcome back to my video. So before we get to the new material today, I want to make a brief review on what we have talked about in last video. So in last video, I talked about the definition of machine learning. Maybe these definitions are just some obscure words. I don't think you need to remember that. And I talked about some terminologies that you will often see in machine learning papers or machine learning project. What is data model, and what is the future, what is the labels, and I also covered some classification of machine learning algorithms, supervised machine learning, unsupervised machine learning, and what is classification and what is regression. So last video is more about a brief introduction to what is machine learning, and in the end of last video, I give this very simple example. If we want to predict the price of a house based on the area of this house, we can use just this linear model. So this is a regression problem. So in today's video, I want to focus on linear regression problem here. So I think I will have 2 or 3 videos on linear regression because I think this is very important. So this is linear regression part 1 here. Okay, so last time we said we used the area of a house as the feature to predict the price of a house. So now let's suppose the model we have so this is the model we have. Now you do not need to care about how we get this model. Of course, I will cover it in this video, and we will go through how we can get the optimal model. I will go through some mathematical calculations here in this video. But at this moment, let's just suppose we get this model. So this is the model we are given, or you get. So maybe it's something like this. So y hat. So here we should also pay attention to some notations here, because sometimes different people will use different notations and it may confuse you. So here y hat is the prediction. I put a hat as the prediction from the model. So this is the model, 2x plus 3. So I choose this number 2 and number 3 because you do not also need to care whether these two numbers make sense. You just I choose these 2 numbers just because they are very simple, 2 and 3. So suppose this is the model we have, and so of course here is the area of a house, and so here is the prediction of the price of a house. And so last time we said we can write this equation in this form. So here you should also pay attention that here omega and x are vectors. So sometimes people put some arrow or some bar inside of vector, but here I prefer not to put them because I write this. So in some books you may say this is bounded. So but here you just need to pay attention that these are vectors here. And we also said we can also write it in this form. So you should convince yourself these two are equal. So here, so what is omega and x? So here x equals to, so we have said that x is the future vector. Future vector here. So we said that all vectors are column vectors in machine learning. And so, I will put the first term as 1 and the second term as x1 here. And we have said omega is the weights and all the parameters. Or sometimes you may say weight. So also, this is also a vector. So you can see how, what is omega here? Because this is nothing but just an inner product or dot product. So this one should be, of course, 3. Because 1 multiplied with 3 equals to this 3. And of course, this is the coefficient before x1. So here, this one actually, this guy is x1 here. Okay, so we can write this in this form. And so here, so in this model, what is obtained from our learning process? So do we learn feature vectors, or do we learn parameters from machine learning? Do you think? I mean, so this one is learned, or this one is learned? Yeah, of course, I think, yeah. So this one, parameters, is learned from training point, training data. From training data, so this feature vector is given. So we have this data. So we have data, that means we know the feature vector of those data, but the parameters is what we don't know. We don't know how to fit the data. So this parameter is learned from the training data. So now suppose I have learned this parameter. So I have learned this one, this BIOS term as 3, this one is 2. So I got this model. So next, we will learn how to get these parameters. Okay, so these are just also very simple examples here. So now let's try to visualize this. So here, I think if I start to make some diagrams, it would make everything become simpler here. So here, this guy is x1. So x1 is the area of a house. So here is y. So this y is nothing but the price of a house. So next, let's suppose our training data or training sample is something like this. As the area of a house increase, and the price will also increase. Okay, we have this training point here. So you can see how I can fit a line in this. Maybe the line is like this. Okay, let's suppose this is the model we just got from here. So this one is the prediction. So here y hat equals to omega transpose multiplied with our feature here. So you can see in this, because we only have one feature here, so in this model we have an interception of 3. So this one, maybe this one is, you can think this one is 3. And also the slope, this curve, maybe it's 2. Maybe it's not something like 2, but yeah, I didn't draw this to scale, so you can think this as 2. So I will write here. So here 3 we usually represent by omega 0, and so here is omega 1 here. So 2 corresponds to this feature vector notations here. So here you can clearly see our prediction in one dimension data is just a line here. So this is just a line, right? Because we only have one feature. We only have one feature, that is area. So here you may ask, so why can't I just predict price by maybe 2 or more futures? Can I do that? Of course you can do that. Of course, we cannot determine the price of a house by just the area of the house. We will determine by many things. Okay. So next, let's consider one more thing. So next we will consider the area of a house and the number of rooms of a house as the features. So now we have 2 features of the data, right? So before that, we just have one feature, that is area. So now we have 2 features. One is the area of house, and the other is the number of rooms of house. So let's do the similar thing. So now let's suppose the model you found is something like this. So here, y hat is the prediction, and also it equals to omega transpose multiplied with our feature vector. So here I will tell you what is omega and what is x. So x is also, so this one, we will by default think the first one of our feature vector is 1, because this one will be multiplied with the bias term in the coefficient omega. So here we have x1, x2. So x1 will be the input, will be the feature of the area. x2 will be the number of rooms here. So omega equals to omega 0, omega 1, omega 2. So you can see I start omega from 0 because in this way omega 1 will be multiplied with, so in this way omega 1 will be multiplied with x1. So this is just for convenience. So you can find that if you do a transpose of omega and then multiply with x, so you will get just a scalar, right? Or just a number. So let's suppose I give you this model. So this model is given to you. So I give you this model means I give you the weights here, because these weights need to be determined by optimization. But now we didn't go through the optimization problem, and next we will go through it. But now I tell you, this is the model, a very simple model. The weights you find 2 to 1 here. Okay. So here, so this one is the area of a house and number of rooms. Okay, so in this way you can also rewrite this one to a more explicit one. So you make the dot product. So this one is something like, so this form is very familiar with you. So it's just a linear equation here. Okay. So now you can see we have two inputs, or we have two variables here. So before this, we just have one variables here, that is x1. But now we have two variables here and here, x1 and x2. So here, sorry. So here we will do the similar thing. We will try to visualize this white hat. So because we have two variables here, x1 and x2, so this would be not on a plane. This would be goes to a three-dimensional space. Let's try to visualize it. So this would be this one, y-axis. So this is our prediction. Sorry, this is our price of a house, not prediction. And we will have two axes because we have two features and we have two variables, of course. So this would be x1, this would be x2. So x1 would be the area of a house, and this one would be the number of rooms. Okay, let's suppose our data is something like this. We have some training point. Okay, this is our training point. And based on this training point, we get this model, and I want to visualize this model. Okay, let's suppose our model is something like this. Okay, maybe it sounds something like this. It's not too scary, but okay, so let's suppose, so this is the model we just defined. Okay, this is the model we have now. And so we can clearly see, so if we want to visualize this is a plane. So this is a plane. So we can see if we have one feature, our prediction is a line. If we have two features, our prediction goes to a plane here in 3 dimension. So next thing you may ask is, what if I have 3 features? What if I have 4 features? What if I have 100 features? What will my prediction look like? How can we visualize that? Okay, let me write this. So the question you will ask is that, can we have features more than 2? Of course, the answer is sure, yes. Of course, we cannot also predict the price of a house by just the number of rooms and areas. We may consider the distance of this house to a school, and we may also consider the number of bedrooms inside of this house. So you can have as many features as you want, but how will our prediction look like in, for example, in 3 features? Can we visualize that? Can we plot the prediction when there are more than 2 features? So here the answer is no. we cannot visualize it, because if we have two features and we have one output, y, we don't know how to visualize it, right? Because the maximum dimension we can visualize is this one, is in 3-dimensional. So 3-dimensional means we have two inputs here. We have two variables. But if we have 3 variables, we don't know how to visualize it. So, but we will give the prediction a name when the features are more than 2. So the prediction will be named as hyperplane. So the model will be named as the hyperplane. So this is a terminology that we will often use in linear regression problem here. So actually, we will call all of our predictions on both 2 features and 1 features all as hyperplane. So this one, although it is a plane, we may also call it hyperplane. So this one, although it's a line, but we will also call it hyperplane. So now we just have one name, right? We call our prediction as a hyperplane. We don't care about how many features we have. We just call our prediction hyperplane here. So it will make our life easier here. Okay, so next, let's review what we have talked about here. So here we have talked about y hat is our model, is our hyperplane, and it equals omega transpose multiplied with x. So it's a inner product here. It's a product between 2 vectors here. Okay, so here let's extend from this one from 2 features to any number of features, maybe to infinite number of features or any number you want, because this is more close to our project, to our practice here, because we don't want to limit the number of features we have. So here omega will be denoted by this one. So omega 0, omega 1, and omega d. So this one belongs to the vector space of course, d plus 1. Okay, here x is the feature vector, and the feature vector is something like this. We said that we want the first one to be 1, because when this 1 multiplied with this omega 0, it will give us the intercept or the bias term. And next one is x1. Of course, we can go to xd. So this one also belong to the vector space of d plus 1. So you may confuse that what is d. So we said that x is the feature vector. So you can see how many features we have in this one here, because 1 is already determined. So we have 1 to d. So d is the number of features. So here d is number of features. So here, if you have d features, you will have d plus 1 weights here, because omega, there are d plus 1 weights in this vector omega here. So in this above example, so in this one, d equals to 2, right? Because we have 2 features here. So this one, d equals to 1, because we just have one feature here. And of course, you can have d equals 3 and d equals 10, d equals to 1000, of course. So now we have generalized this one to any features we want. Okay, so this is the basic linear regression problems here. And I said that linear regression is very basic, but also it is also very important because it will lay a foundation for our neural network in the future. So this one, I can also write this inner product to this form. So I will just circle here. So this one, I write it as 1. So another circle, I write it x1. And I will have xd. So you may find that this one I write here is just this feature vector we have. Okay, so I will call it input layer. And we will have our prediction here, y hat. This is the prediction from this model. And next, I will do a thing like this. I will draw some straight line here to represent that they are connected. How they are connected? They are connected by the weights here. So here I will write, so you can see this 1 will be multiplied with this omega 0. So I will write omega 0 here. And this x1 will multiply with omega 1, of course. And this will multiply with omega d here. So I call this y hat the output layer. So this one actually forms a neuron. So you may not be clear what is neuron at this moment. No worries. I think I will talk about it later in later videos. So you can see I can also represent this regression problem as this as in this form, in this neural form. So we can see here 1, x1, and xd is our feature vector, and we use our feature vector and multiply with these weights here, and then we sum them together. So these arrows actually mean we sum them together, okay, and we get our y hat. So here I can write a sentence like this. Without activation function, so you may not be clear now what is activation function. No worries, and I think I will also talk about it later, but now you just need to think, need to know without activation function. One neuron is actually doing linear regression. So this one, I think this sentence explains why the linear regression is important. Because, you know, without activation function, one neuron is doing linear regression problem here. You may have read some papers or see something someone talked about artificial neural network, and it's just putting many neurons in one model. But if you look them closely, one neuron is actually doing the linear regression, and then what they will have, one more thing is just they will go through a nonlinear activation function. That's it. And that is what the neural network is doing. So without the activation function, it's just linear regression. So linear regression is actually so very important here. So I think that's all I want to cover in this video. And in next video, I will go through some mathematical calculation on how to find these parameters. We will define some arrows and loss function and go through the calculation by a very specific example. Because here, all the models is I give it to you directly. So next we will do something on how to find these weights